Hello and welcome to this guide of resistance soldering. The resistance soldering unit, like a temperature-controlled soldering iron, is an investment. I know there are people wavering before buying an RSU, and others have either not plucked up the courage to get theirs out of the box or put theirs away and left it there for a variety of reasons. This demonstration is intended to show you the principles involved, the benefits, and examples of the technique in use. What you see, though, is my way of doing things, so not necessarily the correct way, but they work for me. You will need to develop ways which work for you, and what you see here will be a starting point. There is an accompanying sheet with references to items I mention in the demonstrations. So let us begin, and we'll begin with the basic principle. A simple circuit. We have a source of power and something in it to work like a bulb. To control the bulb, we have a switch. When we turn the switch on to complete the circuit, the bulb lights up because the filament in the bulb is a bottleneck. It offers resistance to the electricity which has to work to get through, and work generates heat. When you do some physical work like exercise or digging in the garden, you get hot. This principle is used in everyday life. Apart from the bulb, we have the cooker hob, the electric fire, toaster, and kettle. All of these have resistance in the electric circuit which generates heat. We'll compare the electric circuit with our resistance soldering unit. The power comes from the resistance soldering unit, which contains a transformer to reduce the voltage but give a high current or flow of electricity. The switch is on the floor and operated with your foot, which means you still have two hands with which to work on your model. The bulb is replaced by the probe and the solder joint, both of which offer resistance to the flow of electricity. What are the benefits of using resistance soldering? Heat is localized, so you can solder close to other items without desoldering them. The heat is applied quickly, and as soon as you take your foot off the switch, the work cools quickly as well. It's cleaner, faster than the conventional iron. Heat is on demand. Heating is efficient, and the heat penetrates the joint, taking the solder with it. Perhaps the greatest advantage is that you have effectively a third hand, because you hold the work in place with the probe before you solder, during soldering, and afterwards whilst the solder cools and hardens. The foot switch leaves both hands free. A word about safety. The RSU operates on a low voltage which is very safe, though the current is high, so plugs and leads should be able to handle 35 to 40 amps. Other hazards such as flux fumes, hot parts, mains electricity, liquids and so on you should be familiar with elsewhere in the hobby. The RSU does generate a magnetic field, and although I've not come across any problems, if you have a medical device such as a pacemaker and have any concerns, it would be sensible to seek advice. The RSU comes with two leads, a red and a black. The red lead has the probe and a red plug already attached. You can use a pencil sharpener to put a point on the probe or, if you wish, make a different shape. Personally, I've always used a point. It's important though to keep the tip clean or you won't get good contact. Rub the tip on some abrasive paper or scrape it with a knife. The rod in the probe should not be too long. I break a piece off about 2 inches long and it lasts a long time because I rarely sharpen it unless it breaks. I just clean it. New carbon rods are readily available, but in 10 years I've yet to buy one. The black lead has a plug on only one end. The other end is left bare because there are different ways that you can connect the lead to your work. Modelers in the larger scales sometimes solder the stripped end of the lead to their work to give a permanent connection. A steel plate is a common accessory, and to connect the lead, some modelers like to use either a ring or a fork terminal onto the bolt, screwing it down with a nut. Working in the smaller scales, I have found it possible to use a crocodile clip, though some people say the teeth can cause arcing on the work. So to overcome this, I file the teeth off the clip. The clip is not rated for higher current, but works perfectly well for me in 4mm as long as I don't leave my foot on the switch for too long or use more than 2.5 volts. I have made a second black lead with a plug on both ends and used that to connect through a hole in the bolt on my steel plate. The same type of plug is used at the other end into the RSU itself. I have mentioned the steel plate, so we'd better have a look at one. It's something most modelers will have to make for themselves. In my experience, there's a tendency to make them too large and the plate too thick. After 2 or 3 false starts, I settled on a smaller plate, which is about 4 inches by 6 inches, with an M8 bolt in one corner, through which I've drilled a 4mm hole to take the plug. If you do drill a hole and use the plug, put a countersink on the hole, because the plug, once it gets in, can get stuck. The thinnest steel I could get, which remained flat, is about 1.6mm thick, which I got as an offcut from my local stockholder. This is screwed to a piece of scrap oak. Underneath, I drilled a hole for the bolt and attached a piece of non-slip matting. Magnets are used to hold the work onto the plate. Mine are 20mm by 8, long enough for me to get a grip, as the magnets are quite strong. Do be careful with the magnets, because if they bang together they can chip and shatter, as has happened here. People have tried these at exhibitions and been taken by surprise. It's also useful to make a fence against which you can work. This is my first effort with 15mm angle and cube magnets. The double-sided tape I used has not been very satisfactory. I have made more fences where the wood is full length and drilled blind holes into the wood for cylindrical magnets and then trapped them by screwing the wood through the bottom of the fence. There is a problem with the steel plate in that it is a heat sink, and one way to reduce this is to cut a piece of cardboard, cover it with foil and hold it down with smaller magnets in order to make a good connection. The magnets here are 4mm by 4mm, which are small enough not to get in my way when I'm soldering. You then work over the cardboard, through which the holding magnets will still work, but the cardboard itself helps to reduce the heat lost to the plate. There's not a lot to say about tools and materials because they're a little different to those you would use with a conventional iron. I'm not making any reference to solder paste or cream in this video because I just can't get on with them. They work perfectly well for some people, but I've not yet found a way to do this, so I just stick with ordinary solder. I do always have a pot of small solder pieces which I've cut off the reel. You'll see in the pot some thin solder, which is splatter, and some foil. The splatter is made by loading the iron with solder and then throwing the solder at the bench. The foil I made by putting length of solder through jeweller's rollers when I had access to some. The rollers used for forming roofs and boilers don't work for this, as they don't apply enough pressure. You can also flatten solder, squeezing it near the hinge of a pair of pliers or even putting it on an anvil and hitting it with a hammer. Either way, the thin solder cuts easily into small pieces which can be slipped between bits of brass and nickel silver and then soldered invisibly. You don't need any special flux. Use what you're used to. I use Car's Yellow, which I understand is phosphoric acid, and have for years used a syringe with a blunt needle. The needle lasts forever, but the plunger in the syringe gets sticky in time, but the syringe itself is cheap and easy enough to replace. These 3 tools I find useful all the time, not just for resistant soldering. The tweezers have ceramic tips and are heat proof to about 1500 degrees Celsius and cost about £3 on eBay. This means that your best pair of metal tweezers, the tips don't keep getting heated and losing their temper. The micromesh foam sticks are very useful to clean etched parts on the flat and can be cut to shape. The red cubes are cut from old moulds used for resin casting. The rubber is a very poor conductor of heat, and I use them to protect my fingers. On the front of your RSU is a light which comes on when you press your foot on the switch to complete the circuit. There are also 4 sockets, and by putting the leads into the different sockets, we change the voltage of the circuit. This is similar to a temperature-controlled soldering iron, but rather than changing the temperature, think of the lower voltage settings as being more gentle and the higher settings as being more aggressive ways of heating your work. With experience, you will find which voltage settings work best for you. For me, working in 4mm scale, I do most of my work on 2 volts. If I'm working with white metal or delicate bits of brass, I reduce the voltage to 1.5 volts. If I need a bit more oomph, then I'll go up to 2.5 volts. I have occasionally used 3 volts, but never yet used 1 or 4.5 volts. If you're ever unsure about which setting to use, always start on the lower one and work your way up. Before we move on to seeing the unit in action, there is a definite order to using the unit. I recommend tinning parts and doing so whilst they're still on the fret. To solder them, put them in place with a drop of flux and hold them with the probe. Then you press the foot switch. This is usually very brief, perhaps only 1 or 2 seconds, and you may feel the work give just a little bit as the solder melts. As soon as this happens, take your foot off the switch and pause. Keep the probe in place all the time whilst the solder cools. You can then take the probe off the work. If you take the probe off the work whilst your foot is still on the switch, it may well arc. It's been known for that arcing to burn the metal or even evaporate small bits, but this is more likely with the higher voltages. Nevertheless, it can still make you jump. So remember the order, please. Probe on, foot off, wait, then take the probe off. Now we'll start with a couple of experiments. As you will often not see much of the actual soldering taking place, I feel it's useful to get an image in your mind of what is happening. I'll begin with a demonstration which shows how important fluxing and clean metal are. This bit of scrap etch has been handled a lot and picked up dirt and grease from my fingers. When I work some flux over an area, you can see the flux cleaning it and the colour change. I'll now put some solder onto the fluxed area, then to the part which was not fluxed. The solder puddles and doesn't stick to the brass at all well. The next experiment shows how the heat flows out from the probe. I've tinned a circle about 1 inch across and put a bit more solder in the middle to make it thicker. Watch what happens when I put the probe in the middle and complete the circuit. I've added a little red dot to show when my foot is on the switch. You can see how quickly the heat flows through the solder and how quickly it cools and solidifies when my foot comes off the switch. This was done with the RSU set on 2 volts. The speed of the film has not been changed. This is the speed at which it happens. Before we go on, a quick reminder. Probe on, foot off, pause, then probe off. The probe should not get hot, nor, under normal circumstances, should the tip glow. The probe may get warm, so if it gets hotter, give it a rest and allow it to cool. A warm probe is normal, a hot probe is not. If your probe does get hot, you may not be doing something properly. Above all, don't rush. Take your time. We'll begin with something simple. It's often helpful to reinforce a fold in the piece of metal with a fillet of solder. This can be done very tidily with resistance soldering. Flux the fold and add a small piece of solder and put the probe on the outside of the fold. The solder melts, and as with all soldering, the solder will follow the heat, so if you slide the probe one way then the other, you can draw the solder out. Make sure, though, that you keep the probe in contact with the metal until you take your foot off the switch. The same technique also works very well in corners. Tinning is done with a conventional iron. I want to show you what happens to the metal when it's heated. These are overlays for sol bars. Etches are often made from 12 thou brass or nickel silver, and overlays half etched, so typically 5 or 6 thou thick. The ones here are already fluxed. See how they buckle when they are heated, because the ends are fixed to the fret. I always try to tin on the fret so I can run the iron onto the edge and take surplus solder off. It also makes holding the parts a lot easier. I'm going to attach an overlay to a sol bar. As a general rule, where I can, I try to solder from the back. This way, the front is more likely to stay clean. Great Western wagons had two convenient holes in the sol bars through which shunters could attach hooks for horse shunting. I've used these to line up the overlay with the sol bar on my jig, which is made from 2 pieces of copper clad. I've already fluxed the overlay. Remember how the sol bar expanded when I tinned it? Because of this, you should always begin to solder a length in the middle and work outwards. When the sol bar comes off the jig, providing there's not been too much solder used for tinning, the face should be clean. The red discolouring is the result of heat and is not a problem. I'll put a strip of rivets onto this roof of an iron mink. Soldering from the underneath is not possible this time because I can't see precisely where the strip goes and the roof framework is in the way. I've marked the midline on the roof and centre of the rivet strip, which is already tinned. The strip is tacked in the centre and position checked. I've not got it quite right, so I need to nudge it a bit. After that, it's a matter of working away from the centre towards the edge. It's quick and there is little cleaning up to do. As you watch this, think back a few slides to seeing how the heat flowed from the probe. This gives you an idea of how far to move the probe each time. Putting several layers together, or laminating them, is quite simple with resistance soldering. The preparation may take a little while, but you can then solder several layers together at the same time, and the soldering is done quickly and cleanly. Here I'm putting together 3 layers for the doors of a Morgan design iron mink. All the layers have been cleaned, but I've tinned only the middle layer on both sides. Ideally, one should tin both surfaces to be soldered, but on delicate stuff and thin stuff like this, it can often lead to too much solder getting into the joint. The door parts have etched holes to help line up the layers and locate the doors on the wagon itself. I'm using here a piece of MDF which I've covered in kitchen foil and drilled through to hold pins onto which I will build the doors. Soldering follows a sequence to avoid buckling, always working from the middle outwards. The pins on the front face will be filed flush at the end, leaving those at the back to fit the doors onto the wagon. There are 4 layers for this PC model's LNWR cattle box, which I made some time ago. I tinned the back of the top 3 layers, which are the bottom 3 in the picture, leaving the base layer alone. They were assembled, fluxed, and then soldered from the middle, working outwards. The picture of the finished side is from a different kit, but you can still see all 4 layers have been soldered together very cleanly. If you look closely, you can see where the probe was applied. In this case, it wasn't practical to solder from the back. When the side was cleaned, the marks from the probe had all but disappeared. The red colour was on the brass from the original etching process. Confession time, which serves to illustrate another use of resistance soldering, which is to unsolder. Having said earlier, don't rush, take your time. In assembling and photographing the putting together of this door, I did get the middle layer upside down. The scalpel is used to separate the layers and keep them apart whilst the solder cools. You may have noticed a spark when I was assembling the sole bar earlier. We all make mistakes now and then, so don't worry unduly when you make one. You are not the only one to do so. Soldering nuts is a neat little trick you can do with a resistance soldering unit. Rub a nut on a piece of wet and dry to clean it, then very carefully flux just around the face. Try not to get any flux in the thread. Carefully tin the face of the nut a little generously. For this operation I use a higher melting point solder as it gives a stronger joint to resist the shearing force. Another way of overcoming the heat sink effect on the steel plate is to work just off the edge, holding the etch on the plate with magnets. I've cleaned where the nut is to go, so I then flux it, place the nut and hold it down with a probe. I'm supporting the corner of the etch whilst I solder the nut. You can see the solder melting and forming a neat fillet around the nut. With the bolt screwed in, you can see the joint is very firm. I suggest running a bolt or a tap through the nut to make sure any solder is cleared from the thread. My friend Andrew Eaton has used resistance soldering to make track. In the first sequence, he's making V's using a filing jig to hold the rails in place. The steel edge is used to keep the rails straight and provide something against which the probe can push. Andrew also uses cast fish plates from X-Acto scale on alternate joints. After cleaning them carefully on wet and dry, he threads them onto the rail, adds flux and a lump of solder, before using the probe to heat the joint into which the solder disappears. Again, he's used filing jigs to line up the rails. It's quite a simple matter to make neat repairs. Here, the end of the sole bar overlay has not attached very well and is loose. I cut a piece off my solder foil, put in a drop of flux and the solder between the two bits of metal. A quick zap and the job is done. A little blob of solder was easily cleaned off. I've managed to reattach parts which have dropped off painted models this way, cleaning and tinning the part with minimal disruption to the paint nearby. Such repairs would be very difficult with a conventional iron. Some people worry about soldering white metal with an ordinary soldering iron, so to use resistance soldering, which is hot, to solder hard metal to white metal takes a bit of courage to begin with. Continuing with the repair theme, I'm mending a white metal buffer. I'm using a piece of brass rod and have drilled out the stock of the buffer and the buffer head with a hole about 0.05 of a millimetre greater than the diameter of the rod. This is because I've tinned the brass rod with 100-degree solder. It's common practice when adding a hard metal like brass to white metal to tin with, say, 145 solder before using the low melt solder, because the low melt solder does not attach very well directly to brass. 100-degree solder, on the other hand, does attach well to both brass and white metal, so can be used on its own between the two. Having drilled a hole in the buffer stock, I've added a drop of flux and pushed the tinned rod into the hole. Because I want to do this job more gently, I've reduced the voltage to 1.5 volts. The probe is put onto the brass and never touches the white metal. As the brass heats up, the heat passes into the hole and melts the solder. I then slid the buffer head over the brass rod and again heated the brass rod, letting the heat flow along it to melt the solder and attach the buffer head. The brass rod was then trimmed and filed flush. The same technique can be used almost anywhere a hard metal like brass or nickel silver needs to be attached to white metal. If a hole is needed, drill that hole just a little larger than the wire so the tinned wire is a snug fit. Put the wire in the hole, having added a drop of flux, heat the brass and let the heat flow into the hole to melt the solder. You may sometimes see a silver flash from the molten solder. The first picture is of handrails attached to the roof of a David Geen GWR mica. In the second picture, I'm soldering in footsteps to the end of the wagon. The end result in the third picture is neat and needs no cleaning up. The next picture again shows those steps, the end of the handrail and a lamp iron, all fixed using resistant soldering. This is the finished wagon, and all these parts of brass were added using resistant soldering. The instruction plate was tinned on the back, put in place with a drop of flux, and the probe put on the face. Just remember never to let the probe touch the white metal. Try it on some scrap white metal and see what happens. Resistant soldering comes into its own when adding detail to a kit. This is a DNS kit of a Great Western siphon, and on each side, which is laminated, there are something like 40 small detail parts to be added. I made the stand many years ago and find it very useful as it allows me to work on models as though on a flat surface. The crock clip has been attached to the coupling hook, the parts laid out having been tinned first while still on the fret. It was then a simple matter to pick up each part, put it in place with a small drop of flux and attach it to the model. The job of attaching all these parts to the side was a matter of minutes. On this slide, I'm attaching the Filleting mouldings to the end of a GWR steam rail motor. Having tinned the mouldings first, it was a simple job to add them to the end. Resistant soldering can be used on delicate items, but you will do well to reduce the voltage. If you are ever unsure about which voltage to use, always start on a low setting and work up. This is a wheelbarrow from the Southwark Bridge kit. The leg braces are half etched and 1 millimetre across. They've been bent to shape and the ends tinned. The RSU was set on 1.5 volts. I wouldn't usually use resistant soldering on a Paxilin sheet like this, as it can get blistered, but on this occasion the voltage is low and the time taken very, very short. So short that the heat never got near the legs of the wheelbarrow to unsolder them. Not all resistant soldering has to be done on a steel plate. It really is up to your imagination and experimentation as to how you might solder a job and how you might hold your bits of the kit. Here are some examples which need little explanation. The small pliers below the vise are called hackle pliers, used by fishermen for tying flies. They're available from angling shops. The parallel jawed pliers I find invaluable, and the clamp at the bottom of the picture comes normally with a handle, but I've taken that handle off and mounted the clamp on a block of wood and drilled a 4mm hole through the bolt underneath to take a plug. I hope you found this video useful, informative, and perhaps even given you ideas and ways in which you can use resistance soldering. The technique is very useful. It saves time, provides a clean job, and lets me do things which would be much more difficult to do with a conventional iron. It doesn't replace, but is complementary to, conventional soldering. Although it can sometimes take a while to prepare parts, resistance soldering is quick and the results very good. Over the years, I've heard a lot of people say that they have a unit, but they put it away, forgotten it, or left it there because they can't get on with it. I hope this video will encourage those people to get the units out again and give them another go. After all, a resistance soldering unit is not cheap. It's an investment and can give you a lifetime of use. If you can, keep your unit on the bench together with your soldering iron. This way it will always be there, ready to be used. I've never regretted my investment. Finally, please experiment, persevere, and practice. Once you get the hang of resistance soldering, you will wonder how you ever managed without it. Goodbye.